Hey folks, this is Major Jones here to talk to you about how we might go about pipelining the LC3. So in order to do this, we're going to have to understand what a structural hazard is. And in this lesson, we're just going to talk about kind of some high-level changes that we would need to make to the organization of the LC3 to be able to implement that pipeline. If you're interested in seeing the details of how we might do that, kind of more at the component or the gate level, definitely take a look at the follow-on lesson to this, which is pipelining the LC3 version 2. Okay, so to start with, I'm going to go back to that last lesson, right, where we introduced the idea of pipelining and say, okay, in the terms of our factory, we said, oh, we can pipeline it, we can get this performance improvement, and the kind of implicit assumption here was that, for each of these stages, they were able to operate independently of each other, right? A car in the body stage isn't relying on some other component to this factory, which the other stages might have in use at the time. That's a bit of a simplification, right? It might very well be that there's a little parts store, a little parts shop that's providing each of these stages in our factory with parts that they need in order to complete their work. And if we have a parts store that can only service kind of one stage at a time, then even if we've done all of our work to make the rest of this factory pipeline, we're going to run into a problem, which is that we're going to sort of bottleneck around this singular component, which each of these stages needs. And so we call that a structural hazard because the structure of the pipeline has sort of undermining our ability to execute multiple or to build multiple cars at the same time. The way around that is to restructure the design to remove that structural hazard. So in the case of our car factory, that might mean that we create separate parts shops that each kind of support the independent stages. And now, like before, I can have a car in each stage of this factory, and they can all operate independently. Kind of like I alluded to in the last lesson, then our LC3 here, we've got a number of structural hazards that, as it's designed, is going to prevent us from doing any sort of pipelining. So a big one is this processor bus here, right? The very thing that kind of makes the circuit here very elegant gets in my way because if I've got multiple units trying to use this processor bus, at the same time, then I've got that structural hazard, right? And this processor bus, it's used in almost every stage of my state diagram. Additionally, I can sort of broadly separate the LC3 into a couple of key sections, right? I've got my registers up here where I'm storing values. I've got my ALU, which is doing that computation. I've got some memory where I'm reading and writing my instructions and my data. And then I'm going to sort of broadly kind of categorize this section up here as my sort of like the evaluate address portion of the instruction cycle in my LC3. And hopefully when in doing this, I can separate my LC3 into these components that don't have any structural hazards, right? Hopefully I can, if I've done this correctly, which I think I have, we'll see that in processing each instruction, there aren't any instructions that might use more than one of these sections at the same time. We're going to do a couple other things to kind of help simplify this a little bit. So number one is I'm going to get rid of my load indirect, store indirect instructions. Just by virtue of them sort of accessing memory twice, it makes the pipelining a little difficult. We'll reintroduce them in pipelining version 2 if that's a lesson you do later on, but for the kind of the must-do lessons for the rest of this course, we're just going to assume that load indirect, store indirect don't exist. And we can also sort of get rid of the decode phase. We don't need an actual decode step of our instruction cycle because of the fact that we're turning this into a pipeline process. This decode phase was sort of required here as a function of the fact that I have a state machine that doesn't know which state it goes to next until it's able to evaluate the opcode. But essentially all that's going to get hard-coded into my LC3 at this point. Okay, so part of the way that I got to these four kind of sections was in thinking through each of my instructions in my LC3 and asking, okay, what happens in each step of the processing of this instruction? Which components, which sections are used? So you can see here, starting with my operating instructions, add, and, not. Once that instruction gets loaded into the instruction register, the processing requires reading a value out of my registers. So that's number one. Then it goes through my ALU to calculate the actual result. And then I have to be able to write that back into my register. So you can imagine kind of 3 steps where I'm reading something, processing it, writing it back. For my load register instruction, I need to be able to read the register file. So I read where my offset is basically. I got to evaluate the address. So I'm going to add that value to the offset that's in my instruction to determine where in memory I'm getting a value. Then I have to take that value out of memory. So I'm accessing my memory section down here. And then lastly, I can write that value to the destination register to where it's loading. So load register takes sort of these 4 components kind of one after the other. Load effective address and branch are 2 kind of examples of instructions that don't require as many resources, right? Load effective address means I'm going to add some offset to the program counter and store that into my registers. So that just requires this module and this module. The branch instruction really just involves evaluating an address, or not if the branch is not taken, right? But if the branch is taken, then I just have some offset from my program counter that needs to get evaluated and then stored back there in order for that to work. Okay, so if I kind of work my way through all the instructions in this fashion, what I realize is that one, that I get these 4 components. These 4 components kind of show up, and I don't need any further kind of subdivisions for this to work. And also that the most I kind of need on any given cycle, and even for any instruction really, is sort of like one of these 2 variations, right? Load register is kind of the longest in terms of accessing, reading or writing memory, and when I use my ALU, then the most I kind of do is these 3 here, these 3 steps. So then what I can do is create this sort of block diagram for my pipeline down here out of this, right? For all my instructions, I need a fetch phase. And then these 4 stages that come next, 1, 2, 3, 4, are an amalgamation of my longest, the longest pipeline or the longest processes for each of my instructions. So you can see the load register kind of portion here in reading the register, evaluating the address, accessing memory, and then writing that back to the register. If I'm processing one of these operating instructions, I got to read register. Nothing happens in the evaluate address phase. Then I use my ALU, and then lastly I write that back to the register. And for each of these stages, you can kind of see the instructions that would use those portions, in their completion. So load register, of course, uses this phase. It uses this phase. Here I'm accessing memory. There's my load register, and then lastly it's writing to my register. And you can see kind of add and not here for the read register, for the ALU, and for writing to a register. And so again, if I go through all my instructions, I realize that I don't need more than these stages to be able to complete my pipeline. And I can put ALU and access memory together basically because there are no instructions that require both the ALU and accessing memory. It's only one or the other. The last thing I'll kind of note about this is that I have a fetch portion here, which is where I'm getting my instructions. I also have an access memory portion here, which is where I'm doing my load and stores for my data. So in this formulation, I actually have something that kind of looks a little more like a Harvard architecture, where I have separate memories for my instructions and my data. So that's a bit of an architectural change to the LC3. And in between each stage here, you'll see those same symbols from that first lesson on pipelining. These are my registers that basically hold, whatever values that are needed for subsequent stages in order to process correctly. So if I've set this up, then conceptually, as an instruction over here is writing to a register, I might also have one of these instructions that's accessing the ALU or memory at the same time as I have a third instruction that's being evaluated for its address. At the same time, we've got a fourth instruction that's reading some operands out of the registers. At the same time, I have a fifth instruction whose instruction value is just being fetched out of memory. Right? I could have up to 5 instructions basically in this pipeline, one for each of my 5 stages that are all being processed at the same time. And in this formulation, based on the last lesson, right, I could potentially have as much as a 5 times performance increase to my LC3, in sort of the theoretical maximum not necessarily by changing the way that the LC3 is fundamentally, not in terms of changing the instruction set architecture so much, just by sort of rearranging some things to turn this into a pipeline processor as opposed to a multi-cycle processor where it was before. Okay, so in subsequent lessons, we'll use this block diagram to sort of figure out, how this pipeline actually helps improve the performance, and what are some hazards, some things we have to look out for in the processing of these instructions in the pipeline to make this kind of a workable computer. That's all I got for you, folks. I'll see you next time.